morning, everyone. Hopefully everyone's week's going well and everyone's excited for another edition of Environmental Geosciences. Um, Again, just a reminder, the second midterm is going to be next Friday. I wanted to clarify that just like last time, the official exam date is Friday. There won't be a lecture on Friday, October 16th, but the exam, just like last time, will post at midnight on Wednesday. So you'll have Thursday, Friday, and most of the day Saturday to do the exam. I'll send out a reminder about that. But for everyone who's worried about the schedule, don't worry. You'll have an ample amount of time to take that. Almost 72 hours open. But it'll be just like last time. That once you open it, of course, there will be a fixed amount of time to take it. Almost exactly the same as last time. So I'll post a review early next week, and we'll plan on doing a review in class on Wednesday to make sure everyone's on the same page for the second midterm. So what we're going to do today is continue on with our discussion of oceanic and coastal processes and hazards. Reminder, in the last class, we talked about waves and particularly coastal erosion or beach erosion, and talked about the fact that a lot of the activities we've done in terms of keeping transport pathways open, along, for example, Mississippi River, have irreparably changed the sediment transport, starving the deltas of sediments and causing major beach and coastal erosions in the last few hundred years, which is ongoing. And as a reminder, we also talked about the fact that the diversion of these processes actually has caused sediments to grow in other locations where sediment loads aren't being restricted. So, the punchline there is that from a sustainability perspective, there's a lot of concerns about the potential for there to be changes in coastal sustainability related to the fact that sediments are being starved in the deltas, and the barrier and channel islands that are there that usually protect the coastlands, coastal land from major, cyclones and beach erosion have sort of been lost. So today, what we're going to do is pick up talking about cyclones, the process that go into cyclones, what we call typhoons or hurricanes, depending on whether you're in the Pacific or the Atlantic Ocean. And we're going to go through sort of describing what hurricanes are, how they work, and some of the classifications related to them. So some of this might be a review. I think we've all in popular press heard about category something hurricane, right? And in a sense, we'll talk about first just how we can get there. The examples here is that there's basically five. Example I talk about here, independent whether it's a typhoon or a hurricane, is that you're categorized by 5 categories of storm, and the category actually has only to do with the wind speeds, nautical miles per hour wind speeds that are observed in relation to these storms. Have nothing to do with the amount of with the actual size of the storm itself, which is a separate discussion we'll talk about here in a moment. So category 1, 74 to 95 miles an hour. That means you have to be at least 74 miles of sustained wind in order to be characterized as a hurricane. Lower than that, it's a tropical storm, or if the storm is lower than that's a tropical storm. Sorry, if the storm is above that, of course, can be categorized up to a category 1, 2, 3, 4, 5, where the highest category is 157 miles or higher of sustained wind. Obviously, as we talked about in the last class, the wave size, the wave fetch, and the wave duration can all be related to the energy transferred from wind to water. So the amount of potential damage and as a result, the amount of storm surge, the increase in average wave height related to the storms increases commensurately with the wind speed. So as wind speed increases, you can see here that the storm surge will increase as well, and as a result, the amount of damage that can occur along landfall is commensurately increased with the wind speed. What this categorization doesn't really take into account, just to call to your attention here, is the actual size of the storm itself. It really only deals with the wind speeds. In general, the wind speeds do increase with increasing size, and we'll get through why that is here in a few moments. But some of the, basically there's no direct relationship to size. So there is some super typhoon. This is an example of super typhoon Tip. It was actually about the size of the half the United States. Some of them, this actually eventually became a full-blown tropical cyclone Tracy in the Indonesian near Indonesia in the Indian Ocean is actually really small and about the size of a mega city in Texas, like Dallas, for example. So big range in size, not always encompassed in the categorization. Key thing to remember, although I think it's probably common knowledge for most of us, these are hugely destructive storms. They can claim, hundreds of thousands of lives in a single event directly. And of course, the amount of damage and loss of life, economic damage can be pretty much insurmountable. The most deadly cyclone on record is actually the Bona cyclone, this hit India in 1970 and killed about 300,000 people in the Ganges Delta in India. To date, the costliest hurricane actually was in the United States was Katrina, which the damage estimates exceeded $100 billion. That's actually pretty closely tied, depending on how you correct, or pretty closely matched by Hurricane Sandy that hit the east coast of the United States in I think 2011. I'd look up the date for that, but one of these, that or Katrina is the most damaging. Katrina's damage was not just exacerbated on human life and property life, but also property damage, but also the fact that a lot of the infrastructure was damaged, including the major dams and reservoirs. And of course, Hurricane Harvey, and more recently, you're sort of splitting hairs and trying to determine which is the most costly between Katrina, Harvey, and Sandy. Incredible amount of damage on the same level of damage, and it really depends on how you classify the damage and how you attribute the cost of the dollar at the time, which one will be the most expensive. And then the record for the strongest winds was from Typhoon Haiyan, is 195 miles per hour, nautical miles per hour in 2013. Again, I won't test you on any of the specific names, as you've probably guessed by now, but that just gives you perspective here that there are Category 5 hurricanes just about once a decade. There's a Category 5 hurricane, and they can get quite high sustained winds. So the super typhoon Tip, which was in 1979, was the largest ever recorded. Okay, so really what we want to get to is the nuts and bolts of how these actually work. What are the factors that go into making the hurricanes worse? And particularly what factors allow them to do the most amount of damage, or why are Sandy, Harvey, and Katrina, why do they do so much damage, and why was there so much loss of life in those situations? So there are a number of factors sort of necessary for us to see a cyclone forming. The key ingredient, however, is you need to see water temperatures in excess of 80 degrees Fahrenheit. And then that temperature profile has to be across the top 50 meters of water. That's the sort of water depth which those high temperatures need to be sustained in order to keep perpetuating evaporation and allowing the cyclone to form. So if, for example, there are plenty of places on the earth that have 80 degrees Celsius, 80 degree, that would be impressive, 80 degrees Celsius, that have 80 degree Fahrenheit water. But a key ingredient is that profile of warm water is going to extend a significant depth up to about, at least 50 meters. And the key aspect there of that depth is that depth of warm water actually provides a buffer, whereas water evaporates rapidly in the formation of the cyclones. There's an underlying warm body of water that can perpetuate the process. Okay. And that basically allows there to be enough evaporation over a sustained period of time so that the atmosphere can sort of support the winds and thunderstorms. And often these start out as there's a lot of sort of proto hurricanes to start. Most of them don't ever arise becoming a cyclone or hurricane or typhoon. Another aspect here is that in addition to having that large volume and large depth of warm water, there needs to be relatively high humidity. So the water vapor in the air is actually a major component of creating the low pressure systems that can cause the continued development of the large clouds and the rotation of the clouds. So if you remember the mass of the atmosphere is about 78% nitrogen, 21% oxygen. Just to keep that simple, the mass of nitrogen is about 28 grams per mole. The mass of oxygen is about 32 grams per mole. As a result, let's just keep the math simple as 3/4 and 1/4. that means the mass of the atmosphere is about 29 grams per mole. So when water evaporates, when there's more water vapor in the air, or there's a higher humidity, that actually, the mass of water is about 18 grams per mole, and that means that the mass of gas in that parcel of water, if it's water saturated, actually decreases in weight, and that's why you call storms are low pressure systems. That low pressure causes air to move into the storm center, and then and large enough systems actually can cause a rotation because of um, circulation of the rotation of the Earth. Sorry. So in addition to this, you need to see really warm water, high humidity in the atmosphere, and then you see rapid cooling in the higher parts of the atmosphere. So the key aspect of this is that the water will evaporate rapidly, and actually as a result will cool. The key component to this cooling is something called the adiabatic lapse rate. That's a fancy word, but basically what it tells you is something you probably already know. If you go to higher and higher elevation, it gets cooler. Depending on how much water vapor is in a parcel of the atmosphere, that's about 6 to 9 degrees Celsius per kilometer. So relatively rapid cooling rate. And what we want to see here, if we're looking to make a hurricane, which I don't know why we would do that, is again warm water, very high humidity atmosphere, and then above that an area that's quite cool, which can cause the cycle to sort of convect and rapidly rise. And then the last components, this is the component that kind of eliminates most of the sort of proto-hurricanes or proto-cyclones from becoming real, is an absence of disruptive shear winds. So what we want to see is a prolonged calm period with some atmospheric disturbance creates a storm and causes evaporation, but not a lot of activity in the ocean at that time. For example, often you'll see, if you watch the Weather Channel, you'll see 2 or 3 hurricanes starting, and actually most of the time there's a greater potential for one big prolonged hurricane by bringing one disturbance in a given ocean, as opposed to multiple ones, which kind of cause a lot of shear winds and generally can disrupt the hurricane from sustaining these conditions of hurricane or cyclone growth. So it doesn't have to be another hurricane. It can be just an abundance of storms, strong winds or coastal winds in an area can actually sort of just cause shear and disrupt the prolonged occurrence of hurricane formation. And then the last sort of key ingredient here is that there has to be something that starts this disturbance. Everyone's heard the phrase, somewhere in Africa, a butterfly flaps its wings, as these stories of how everything gets rolling, and that's obviously not how a cyclone really starts. But there often has to be some disturbance. It can be a localized thunderstorm, a minor weather disturbance, change in wind directions. These disturbances can often cause high amounts of evaporation in an area, disturb the weather pattern, and actually become the seed for a cyclone. And then the key aspect here is that all the cyclones start within about 350 miles from the equator, or basically well within the tropics where most of these events happen. Otherwise, areas above that just can't sustain typically the higher degree, this component, the 80 degrees Celsius, 80 degrees Fahrenheit waters, the top 50 meters of the ocean. So there's speculation that could change with climate change. As the ocean gets warmer, that region could expand, and as a result, there could be more cyclones. But in reality, today, about 350 miles from the equator is the limit. So let's look at this in terms of the anatomy of the actual event. The key thing here is that the cyclones have to begin as some tropical disturbance. It could be something as small as a daily thunderstorm causes enough disturbance to create this sort of convection cycle. So these can be areas of unsettled weather. It can just be winds. It can actually be thunderstorms. Most commonly, it's thunderstorms which themselves have a low pressure system because they have a high amount of evaporation in them. And basically that high amount of evaporation over an area of warm water, again, at least 80 degrees Fahrenheit across this body of water, 50 meters deep, that can cause the rapid evaporation you're seeing here in the red arrows across that region. what happens is, as that water vapor leaves the ocean, comes up in the clouds rapidly, particularly the high temperature differential, it relatively rapidly cools. Okay, that because of that adiabatic lapse rate, where it rises up a few kilometers, will cool, and some of that water will precipitate out, and you'll often see, these sort of pairings of rain bands, sort of cyclical bands of rain around the hurricane's eye, which will be massive evaporation with little periods of rain. But of course, some of that moisture is actually drawn up into this formation of this sort of this large cirrus shield cloud, which is what we sort of see as the hurricane. So it can have a lot of rain, and often very intense rain in it. But the key aspect here is that some amount of that evaporation is actually making its way up into this sort of large shield cirrus cloud that can be really large and encompassing. And most of the evaporation is across that entire plane of the circle, and it's actually the rotation of the Earth that causes the cyclone to start to change and bring on that cyclone. The cyclone, the CYCL, is a result of that sort of rotation, is where the cyclone comes from. And the eye of that hurricane can be a combination of evaporation, but most of that is actually the downwelling of relatively cool dry air from above that gets encompassed by the cyclone. So the key thing here is the warm air has to rise from the surface of the ocean. That, as I mentioned, that reduces the mass of gas in the parcel of air, and that causes the low pressure system, which brings air in from the outside parts of the storm, from outside the boundaries of the storm, and basically that process along the rotation of the Earth is why this will spin. You'll notice that as this hurricane starts to move, it's typically carried by something called the Hadley's convection cells. Throughout the entirety of the surface of the Earth, there are areas like the equator where there's intense evaporation. There's areas like the tropics where there's intense precipitation. And as a result, there's always this sort of directional movement of wind away from the equator towards the poles, which is what's typically carrying the hurricanes away from the area near the equator where they're formed. And the last component I'll talk about here is there's something called the Coriolis effect. It's the actual fact that if you throw a dart a really long distance, or move a parcel of water on the ocean a long distance, as the Earth rotates, it can actually cause an apparent bend relative to the surface of the Earth as that parcel of mass migrates away. And that's sort of what causes the direction of these hurricanes to move as they go. So, again, the primary energy source is all driven by the evaporation from the ocean. It's sort of a balanced cycle where ultimately that rain's all going to condense as clouds and rain out, either a lot of it across the ocean or some of it in landfall. So, sort of similar to some of the other factors we talked about, tsunamis, as that water sort of reaches the land masses, it generally starts to slow down. A lot of that's because of the fact that there's more turbulence related to the waves we discussed earlier. And in most cases, what happens is that this cloud undergoes a lot of evaporation, starts to move away from the equator because of those Hadley convection cells atmospheric mixing, can be diverted in direction by the Coriolis effect. And in most cases, as it moves further from the equator, I'll use the northern hemisphere as an example, it's going to cool down, and actually it'll run out of more evaporation that sort of powers the system. However, as particularly examples of a Hurricane Katrina and Harvey, sometimes it can actually encounter places like the Gulf of Mexico, which are sort of, if you look at the map of the Gulf of Mexico, it's a sort of a surrounded body of water, so it doesn't mix very easily with the oceans, and as a result, it has potential to become hotter than normal in warm times, and actually can be cooled more than normal. It doesn't mix as much with the Atlantic in cool times. And as a result, pretty often late in the summer, we've experienced some very large earthquakes. Totally drew a blank there. Very large cyclones, because as the cyclone's moving closer to the shore rather than moving further north and cooling down, it's actually encountering a body of water that's been sitting there sort of stagnant and hasn't been mixing with the ocean very much, and as a result is often warmer. So typically, the cyclone should be cooling down, or should be slowing down as they encounter cooler water. In the case of Harvey and Katrina, they actually were exacerbated and become intensified, picking up more rapid evaporation because it's going over warmer water. Um, so, in that situation, most of the flooding, loss of life associated with the cyclones are actually due to the fact that the acceleration as it's moving closer to land increases the winds, increases the amount of rain, and actually the combination of those two things increase the storm surge, cause there to be sustained higher waves, and most of the damage, particularly from flooding, is, as a result of those activities, loss of life is caused by the storm surge itself. Um, uh, Most of the issues are tied to local rises in sea level, low-lying areas, or areas that don't actually allow good incorporation of water into the groundwater. So we'll talk about this a little bit later here, but areas where there's a large urban development where there's a lot of cementation on roads and impervious surfaces, or in areas in low-lying areas, valley bottoms can be pretty rapidly flooded in areas where there's high storm surges. These can often be, back a few miles from the actual coastline. Um, Another aspect of this is the fact that, particularly in examples like Katrina or Harvey, is that the fact that the winds and the surge are actually increasing and accelerating as you get near the coast. That can sort of push the surge, inland greater than is typically expected. So oftentimes, we actually haven't developed the suitable infrastructure to handle these really intense storm surges, because historically we've built with an expectation there was going to be a need for breakers, within few kilometers of the surface of the coastline rather than in deeper. And as a result, you can often see the water depths near the coast can increase by as much as 10 meters. That's more than 30 feet for perspective. So that can be a really devastating amount of flooding. Again, most recently, in the last, in the century, demonstrated by major flooding events in areas like, Houston, New Orleans, and even New York City in terms of Harvey, Katrina, and Sandy. Obviously, tides have a relatively minor role compared to the wind volumes, but of course, if these happen to coincide with periods of higher tides, the storm surge can be more damaging. A lot of that is when it makes landfall, and in the case of Katrina, it happened to be a situation where it coincided where everything that could have went wrong did. So in general, as the cyclone or hurricane reaches land, it tends to, once it reaches land, it's deprived of the more evaporation that's sort of serves as its energy source, and weakens. I mean, obviously, living here in Ohio, we recognize that we regularly see major rainstorms. Some of our biggest rain events in a year are tied to hurricanes that fizzle out over the Gulf, and basically still can travel great distance and bring large amounts of moisture, even as far north as Ohio or Pennsylvania, New York, something like that. But in general, in these situations, the storm is dramatically weakened. You usually don't see sustained winds. Even though we'll see rain in places like Ohio, you won't see sustained winds above 30, 40 miles an hour here typically at all from these tropical storms as they downgrade from hurricanes. This here is actually a map of of all the cyclones. So hurricanes in the Atlantic, typhoons here in the Pacific. This is between 1985 to 2005. So give you a track of all the locations. You can see there's a large scattering where these things eventually end up, throughout both the Atlantic, the Pacific, and whatnot. But a few things I want to call your attention to. Notice that they all form very close to the equator. Most of the intense activities within, again, 350 miles of the nautical miles of the equator. And another thing I want to point out to you here is that the track is usually with the trade winds near the equator. You see they're often going to the west. That's because the easterly trade winds are coming east to west in this part of the world. The opposite's true in the southern hemisphere. So notice that the cyclones are typically moving towards the west, and as they start to move north in the northern hemisphere, they're often deflected back away, and that's the known as the Coriolis effect, which deflects them back away based on the fact that the rotation of the Earth actually sort of moves out from under the hurricane, if you will. The other thing I wanted to call to your attention here is the fact that notice the large amount of latitude in the northern hemisphere. And this is largely caused by the fact that the ocean currents and the wind patterns are being partially affected by the landforms in the northern hemisphere. Most of the land masses in the northern hemisphere, and as a result, the cyclones that form in the southern hemisphere actually, even if they start to move away from they're moving east to west, but even as they start to move away, towards the South Pole, they sort of get blocked off by the fact that there's more of those shear winds and currents that sort of block out a lot of the great shear and basically degrade the intensity of the cyclones. The Southern Ocean itself is actually, because of the absence of land masses, there tends to be a much greater perpetuation of wind and waves, and as a result, sort of the much more violent has a way to sort of cause shear and disrupt the cyclones from actually migrating further to the southern ocean. Um, but this called your attention, hopefully, that most of the hurricanes, typhoons, cyclones, all are within about 8 degrees north and 15 degrees south of the equator. And largely that, again, just to reiterate, goes back to the fact that it's where the surface water can exceed 80 degrees Fahrenheit for a sustained depth, at least 50 meters. Key to being there is that in order to get the cyclone started, you have to have a large amount of sustained evaporation, and that evaporation needs a large mass of water that can be heated up to sustain that process. So, little areas like, the Great Lakes, for example, we can get 80-degree Fahrenheit water, but they really don't have enough massive water to sustain the hurricanes. There's a huge amount of evaporation and energy transferred in these events. Years of, for example, some of these hurricanes, cyclones, interchangeably using these terms here, can actually transfer as much energy as annual energy output from the United States. Always a different form of energy. So, for perspective, there's a lot of concern about how cyclones are going to change in climate change, and quite frankly, we don't have a very good understanding. The forecast modeling suggests that storm frequency and intensity both will increase, but for perspective, there was a period of a high number of cyclones and particularly hurricanes in the Atlantic in the 2000 to 2015 range. Last few years have actually kind of calmed down a little bit. That doesn't mean climate change has gone away. There's a great amount of variability and uncertainty in the number and frequency of events like this. From a sustainability perspective, what I'd like to highlight, though, is that what's changed more so than, or even more so than the intensity and frequency of storms, is the fact that there's, again, back to the earlier part of this lecture from Monday, there are significantly greater number of people living in coastlines. We have not necessarily done a good job of maintaining sustainable strategies near coastlines, which we'll get to in a second, regarding controlling erosion, allowing sediments to keep the sort of channel, barrier channel islands and whatnot from eliminating the amount of erosion and surge that occurs in those areas. But just from a big perspective on the cyclones, the North Atlantic has a sort of semi-distinct season. This has been one of the controversies. People think with climate change, this is going to actually expand a little bit, maybe become more intense during this time, but maybe come a bit earlier, a bit later. But in the North Atlantic, almost all of what we'd call hurricanes in that area occur between June 1 and November 30th, and they sharply peak towards sort of late August through September. So we're actually coming out of the peak of a hurricane season now. Similar patterns in the Eastern Pacific, so that's over near California or Mexico, but the Northwestern Pacific and the Indian Ocean actually don't have so much of a seasonal aspect to this. Most of those are areas where the waters remain warm enough to create cyclones throughout the year, and particularly in the Northwest Pacific, you see that there's not really a seasonality. It's sort of the conditions are right in many parts of the Northwestern Pacific to create what would locally be called typhoons throughout the year. So the Southern Hemisphere does, this is getting areas where you're getting a little bit further away from the just like the North Atlantic, getting a little bit further away from the equator. There's more of a cyclicity to this as well, and that is sort of almost the exact opposite of ours in the northern hemisphere, which is the southern Pacific. November till the end of April is the typical time frame for what are locally called cyclones in that area to get going. We mentioned this earlier in terms of preparing for human adaptations to climate change. Clearly, this is one area where you're quite well aware of the fact that the global temperatures, or the average temperatures in the surface waters throughout the global ocean have been increasing, and you can see here that this shade of red is pretty prominent in this graph of about a 1.5 to 2 degrees Fahrenheit increase in temperatures across most of the Atlantic, certainly in the southern Atlantic, most of the Indian Ocean. In fact, outside of this area right here, have experienced about 1.5 to 2 degrees Fahrenheit increase. Some localized areas that have gotten a little bit cooler, and around our coastlines about a half to a degree increase in temperature. But on the aggregate, as we know with climate change, there is an increase in temperature, and as a result, to reiterate this point, we expect the latitudes at which hurricanes can form to be extended as the ocean temperatures increase. This will potentially lead to more cyclones, hurricanes, and there's also a fear that given the fact that the energy is derived by how rapidly the evaporation can occur, that by having higher temperatures, you could experience more intense hurricane events, than there was in the past. But for perspective, again, you always have to remember with these cyclones, hurricanes, typhoons, etc., is that there do appear to be some cyclicity in the amount of these events on an annual basis. I think the peak of cyclone activity was actually in the early 1960s. We're getting back to that area now. So there's a lot of debate about just how it will affect the number and the intensity. But the reality is, there is believed to be a significantly higher risk of ongoing cyclones based on the fact that the temperatures of the global ocean are increasing. Clearly in the case of Katrina and in Harvey, the temperatures in the Gulf of Mexico have been rapidly intensified in the Gulf in these years compared to a 1960 to 1990 baseline. Within the Gulf and even right along just the margins of the coastline here, it's not just 1 to 2 degrees Fahrenheit. It can actually be up to 7 degrees depending on the year. Increased temperatures in the Gulf, and both Katrina and Harvey, the times where these hurricanes made it to the Gulf, in mid-September, where things should be cooling off but haven't, and actually in often cases are much higher than expected. That's where that 80 degrees Fahrenheit threshold's there, and you can see that storms intensify and actually lead to much greater events than would be expected, in this coastline. So a lot of the devastation with Harvey and Katrina does have directly to do with higher surface temperatures in those areas. Sticking on the using Harvey as an example here, Harvey was incredibly devastating to the Houston area. I don't think we really probably talked about it enough and got as much of attention as public publicity as possibly it should have. But to call your attention here, some of these examples. Here's a scale here, 10 miles. Some of these are 40 miles from the coastline of in Galveston Bay, which are 19 feet over the river channels that are of course engineered to actually prevent moderate flooding events. So this is a profound storm in Harvey that did an incredible amount of damage along this sort of main channel through eastern Houston. You saw routinely feet over the flood channel, being 10, 20 feet over the flood channel, led to pretty devastating flooding. So we already highlighted the fact that some of the main reasons the flooding was so intense and the storm was so intense in this area is because of the fact that the Gulf was hotter than expected, that where it should have been cooling down, and in fact it was accelerated by the fact that there was almost 7 degrees Fahrenheit higher temperatures. But there's some other factors that we have to consider here, for perspective on why Harvey ended up being so bad. So, just to give you a perspective on this is Galveston got 25 inches of rain basically in this sort of week-long period. Another factor that led to this being so intense is the fact that the storm sort of got there and stalled, sort of fueling itself off of the high waters, high temperature waters from the Gulf, and sort of stalled over the area, and ended up being a really prolonged period of rain. It wasn't just sort of moving through, but this is this is uh, this is a perspective of all the way from Friday to Saturday, uh, Tuesday up to Wednesday of the sort of tracking of the main eye of the storm. So you see it sort of just stalled over Houston, didn't really move very fast. Um, but on the aggregate, this is the rain in a given as the storm passed in 25 inches. This is the total rainfall down here in the grayscale, where you saw 50 inches or more of rain throughout the period of time, right? So that's an insane amount of rain that really is not much help doing much with at all. So there's a lot of factors besides the Gulf being hot and the fact that the storm sort of stalled over the area that led to the extreme amount of flooding in Harvey. And really, a lot of it comes down to understanding the actual local geology of the area. So this is a map of a soil absorbativity. And basically, what it looks at is how much water can, or how easily water can percolate into the soil of a given area. So you can see here, there's a range of 0.1 or less up to 1 in terms of the sorbativity. And basically, what you're talking about here is in order for a soil to take on a lot of water, there's some characteristics that are important that allow soil to take on a lot of water, and that's largely based upon something called porosity. That's the amount of space in between grains or in between soil. The more space you have in the soil, like for example, poorly sorted gravels or big chunks of rock tend to have a lot of space and can accommodate a lot of water. Really fine grained silt or clay tends to have very low porosity and can't take on much water at all. So there's a range there based on porosity. The other one is basically the amount of organic content. The amount of organic content and vegetation can also increase the amount of the capacity to take on more water. So more organic content tends to be good. And certainly high amounts of vegetation are really important for actually increasing the amount of water that can be taken on absorbed during events like this. The key aspect of that vegetation is something called evapotranspiration. So water percolates in, the plant has access to water, it thrives, it sort of kicks its growth processes in, and it actually breathes water vapor back out into the air. Okay, so if you look at a map of the United States, there are areas that have very, very low porosity. Some of them right down here in Houston, which is actually an member of low. Ohio here, some of it's the eastern half of Ohio in the Appalachian Basin has a lot of different sandstone rocks, and glacial till is very high amount of absorbance, can bring a lot of water in, has a capacity to store a lot of water very quickly. Eastern Ohio, where you see the geology changes, less glacial till and more fine grained sedimentary rocks, very modestly low. But in essence, these coastal plains around Houston are areas where you have really fine grained sediments deposited sequentially for long periods of time. They get packed and packed and packed down, and these really fine grained coastal areas tend to have very fine grained rocks, but they also tend to have very low organic content. And because there's such an active area where the tides come in and out, and where where they've been affected by sea level changes over time, they tend to have a limited amount of vegetation that can both handle that sort of violent nature of the tidal zones, and also can handle, can basically are adapted to live in both areas of high erosion and also high salinity from seawater. So most of the country has potential to take on a lot of rain. We'll talk about some of these other ones very, really quickly here. Not necessarily relevant to the discussion of Harvey at all, but or even mostly to cyclones, but areas of large volcanic provinces, such as or metamorphic provinces, tend to have relatively low absorbativity. So a lot of California, a lot of the Arizona, New Mexico, they also don't have the capacity to take on a lot of rain. But most of the rest of the ones that are out here in the middle of the country have to do with shales and really fine-grained sedimentary rocks that prevent us from bringing much water into the soils. But Houston, right across the coastal plain over to New Orleans, all in an area where the really fine-grained, low organic content sediments are pretty much the worst case scenario for taking water on. And in addition to that, it's also the fact that, again, this saltwater freshwater interface leads to a very small niche of the type of plants that can live there and thrive. So the big factors I'd like to call your attention thinking about sustainability is this is an image of 1940 Houston. The areas here are the percentage of impervious surface. So that can be parking lots, that can be constructed buildings, roads, basically anywhere where water can't drain into the soil naturally. And if you look here in 1940, that area is pretty small. If you've been in Houston, well, all of them, it's sort of the inner belt there. And there was a massive amount of areas around here where water could basically percolate into the subsurface. If you flash forward to, no pun intended there, to 2017, you'll notice that the area of sort of urban development around Houston is expanded dramatically. So this is an area now where there's a really high percentage where it's almost the entire, the county, I'm drawing a blank on the name of the county there. I want to say Harris, but I'm not sure I'm right about that. Has between 25 to 100% impervious surface where no water that falls can actually penetrate into the subsurface. And the other areas, the outbelts, of course, are seeing similar amounts of development here. So you can see across this entire region, you went from almost 0% impervious up into this light green, which is a few percent, and all that sort of contributes. But these areas of major, urban cities have really devastated the amount of recharge that can get into the ground. So the development, mega trends that can influence society. One of the big ones here is that we need to consider here in regards to hurricanes specifically and flooding is the development of large urban centers or mega cities, as some people call them. And Houston's one of the largest in the United States. The massive expansion in those areas, with not really a lot of the planning to put in a lot of green spaces, lead to really high percentages of impervious spaces. And when you get a rainfall event of 50 inches of rain, it's hard to believe anything could have prevented this. But clearly, not allowing the ground to actually serve as one of the reservoirs that takes some of this water away from us, exacerbating the flooding is a major consideration that planning in the large urban areas needs to recognize. The other aspect there is that this idea of impervious surfaces is new, right? We knew for a long time we had gray water sewers that would basically collect the water and have a sewage pipes that can drain this out to the Gulf or other bodies of water regionally. But when you get so much rain, 50 inches of rain like you saw in this example, you actually sort of put a plug of water in the bottom. There has to be a gradient for the water to flow down in order for that to occur. When those amount of rain, those large rain events occur, basically you back the system up and the water wasn't getting out. From the water quality perspective, that's an issue that comes up in a lot of flood areas after natural disasters in terms of water quality. That the fact that the sewers aren't draining or backing up obviously means that most of the water you see, people often are dying of waterborne illnesses or even dehydration after, in the days after disasters like this. You see all the, it kind of goes back to that old phrase, water everywhere, but not a drop to drink. The other component of this that needs a lot of attention is that this urbanization doesn't just lead to impervious surfaces. Urbanization means we're ripping out natural vegetation. We're often clearing forests. We're seeing land use changes of deforestation to build homes and parking lots and things like that. And one of the things that's really relevant in this part of the world in the Gulf is actually something called switchgrass. So, here's the average height of an American male, 5'8". Switchgrass here is actually about 14 feet tall. If you look at it, it's kind of interesting that this is low-lying grass. I don't know, maybe 4 or 5 foot tall, so along a lot of the coastlines. It's very well adapted to live in brackish environments, sort of freshwater, saltwater interfaces. And it has these incredibly long roots. So I mentioned, evolved to withstand tidals, changing tides, evolved to withstand storm surges, evolved to actually understand to tolerate long-term changes in sea level, high and low in that tidal zone. The switchgrass is sort of a pretty important part of the ecosystem where those really extended roots and its its genetics actually allow it to A, withstand large changes in water, not be eroded away very easily, and actually very important in preventing beach erosion as well, but also adapted to live in that saltwater freshwater interface where it's not affected by that. Most of this urbanization actually, removes large swaths of switchgrass. It would have stopped the hurricane from pouring down. It would have stopped the hurricane from flooding, but it probably would mean we would see less major episodes of erosion after flood events like this because more of that would be in place. And actually, particularly going back to the idea of coastlines in places like New Orleans, for example, that becomes a major concern because of the fact that it prevents some of the loss of barrier islands and things like that. And that's a major focus in Houston. These have been heavily eroded by this storm event. So all these factors are things to consider, but the lack of water, the lack of capacity for water to be introduced into the subsurface and stored temporarily as groundwater means a lot more of the water is available for flooding. It leads to a lot more overland flow, which does great loss of life, lots of property damage and damaged infrastructure. And more importantly, in this area, long-term effects is there's major changes in erosion, in coastal erosion, in the sort of nearshore seaways, where in fact the longest effects of Harvey are not just the incredible devastation, but also the fact that the next time an event like this occurs, there's been more erosion and more loss of sort of the natural barriers to some of these problems that are no longer there. So I think that's a natural break in the lecture for today. I'm going to stop there for now, and on Friday we'll pick up with coastal upwelling and sort of wrap up our discussion of coastal processes. I hope everybody has a great middle of their week, and I'll see you all on Friday if there are no questions.